In this video, what we're going to cover is the mechanisms by which addition of water to an alkyne leads either to the ketone or to the aldehyde, depending on whether you're going via a Markovnikov process or an anti-Markovnikov process. And the idea for both mechanisms is simply that the addition of water proceeds as you would expect, as though this were a double bond, but the enol that you form then ends up tautomerizing. And there's a little bit more going on with the acidic mercury catalyzed conditions than there is with the borane. The borane addition is really truly going to be the same as with the double bond, and then the oxidation step is exactly the same as the double bond, and then you have a simple tautomerization in base to give to the aldehyde. So this one's more straightforward. This one's a little dicier. Let's start with this one. This triple bond will attack this mercury while the pair of electrons that's on the mercury will come back and cause the usual little triangle to form. The mercury cation that's formed has, of course, a formal plus on it, but what that means in practice is that the two carbons attached to the mercury are more delta plus than you think. So even though there's a plus on the mercury, in practice you're going to end up attacking one of the two carbons attached. And if there's a difference in terms of their stability, then the water will add at the more stable carbocation. So even though this is vinyl and relatively high energy, you'd prefer to add at the secondary as opposed to the primary. So water comes in, which causes the mercury to leave, and then that forms in the immediate short term a protonated water molecule attached. Temporarily, we find ourselves in this state with a protonated water just having added and a mercury nearby. So now the water comes by and abstracts one of these hydrogens, thereby getting rid of the plus charge that's on the oxygen and now creating an H3O+. But before this water gets a chance to go too far away, what if the double bond comes by and abstracts that hydrogen? And this is likely to happen, again, it's right there, but it's also likely to happen largely because this oxygen can then cause some electron density to flow into that double bond, making that double bond more reactive. The nearby oxygen causes this kind of transformation to take place. And this is, I would describe, a keto-enol tautomerization in disguise. It's in disguise mostly because of the presence of the nearby mercury. But now the odd thing is that you've got this mercury that's sitting here, and you've got this oxygen that desperately needs some electrons, and the mercury is perfectly content to give up some of those electrons. So what happens is that the mercury just plain leaves, and what was the carbon-mercury bond now becomes a double bond, and that of course causes these electrons to kick back up onto the oxygen, which then of course leads to a official enol. So now we have the enol sitting here. What happens if the enol once again attacks a nearby H3O+, pulling off the proton? Well, of course, that's going to lead to one last protonated ketone. And then, of course, we have one final molecule of water come by and remove the final proton, and that completes the transformation and ends up as the final ketone. So this is now a complicated mess, as you see, but the initial step is attack of the triple bond on the mercury. That leads to this cationic intermediate, which gets attacked by water, that then forms this protonated water intermediate, which then gets deprotonated. And now what we're doing here is basically the start of a keto-enol tautomerization, where essentially you're protonating this double bond, which then leads to what amounts to a protonated ketone. Rather than deprotonating at this stage, what happens is the mercury simply leaves, and that causes the electrons to become a double bond. So now we are officially at an enol, and then this last sequence of steps that I've now circled in red is an actual keto-enol tautomerization. So in my mind, the key features of the process are that you have a standard addition of water, that's what's happening through here, and then you deprotonate. And now you do what amounts to a keto-enol tautomerization. It just looks weird because the mercury's bound. And then once you arrive at this enol, then you do a normal keto-enol tautomerization, and you end up at the ketone. So in essence, the reason why this all happens this way is because we're in strongly acidic conditions. So this is the process by which you arrive at the product that involves strictly cationic or neutral waters along the way. So every time you have a neutral water, which then picks up a proton, which then gets deprotonated and so on, but we're going through cationic oxygens, plus charges on the oxygens, no minus charges. And this is by distinct contrast to what we're going to do with the borane, which involves purely anionic processes. So either the oxygens are neutral or they're minus. Under acidic conditions, the oxygens are neutral or they're plus. Mechanistically, the process for hydroboration is much more straightforward. You're first going to do the hydroboration in such a way as to put the larger R groups on the boron away from the internal parts of the triple bond. So mechanistically what happens is you arrange the H, the smaller group, over the larger carbon, and you put the boron over the smaller smaller carbon, and you go ahead and perform the usual hydroboration sequence whereby the electrons from the triple bond flow to the empty orbital of the boron as the BH bond is delivered to what would be the more stable carbocation. That immediately forms the expected hydroboration product. At this stage we have the hydroboration. Now a little bit of magic happens that I'm not going to describe, during which the oxidation step takes place that converts the boron into an oxygen. But the upshot at this stage is that you have arrived at an enol, and this is an enol that exists in the presence of a substantial amount of base, because of course the oxidation part takes place under strongly basic conditions with a bunch of hydroxide. So you can immediately deprotonate at this position, which forms an O-. You can either draw the other resonance form. The acid-base reaction between the hydroxide and the OH creates a water molecule, and you can go ahead and simply draw this sequence of arrows to liberate the desired product, which is going to be this aldehyde as drawn, plus of course leftover hydroxide. And of course these products are indistinguishable from each other. There's a butyraldehyde and a butyraldehyde. This sequence of steps right here, of course, is the tautomerization. In the case of the borane, this is an utterly standard hydroboration oxidation reaction, at least for the first part, which then leads to this enol, and then the enol tautomerizes, and it happens under basic conditions, so we have either formally neutral oxygens or formally negative oxygens all along the way. You could draw this tautomerization slightly differently by having the resonance form rather than the more complicated arrows, but the upshot is going to be the same. The only way in which the hydroboration of alkynes is different than alkenes is you tend to need relatively large boranes, so you could either use the dicyamyl borane drawn or perhaps 9BBN, which again would tend to be abbreviated this way. In any event, using a large borane is necessary with the alkynes, but you do a large borane for the hydroboration parts, you do the oxidation, and in the workup steps it gets converted into the anti-Markovnikov addition of water, which in this case leads to the aldehyde. This is of course by contrast to the cationic addition of water via mercury, and again the way the mercury addition works is completely standard except for the introduction of mercury intermediates that behave a little bit differently, but the idea is the same. You add water in the standard expected way, tautomerization takes place. In order to make this all work mechanistically, I like to think of it as two different tautomerizations under acidic catalyzed conditions. But big picture, if you add water to an alkyne, what happens is first you do an addition of water and then tautomerization takes place. And since what you make in the first step is an enol, what you end up making at the end is the tautomers of it, either an aldehyde or a ketone, depending on whether you added water via the anti-Markovnikov pathway or the Markovnikov pathway.